D block elements is the collective name for the groups 3 to 12, in which the d orbitals are progressively filled in each of the 4 long periods. As the d block elements lie between the s and p block elements, they are also referred to as the transition elements. The f block elements, on the other hand, include the 4f and 5f series of elements, in which the 4f and 5f orbitals are progressively filled. They are often referred to as the inner transition metals because they involve the filling of the inner 4f or 5f subshells. There are mainly 3 series of transition elements. They are the 3D series, the 4D series, and the 5D series. The 4th series, the 6D series, which begins with actinium, is still incomplete. The first transition series includes the elements from scandium to zinc. The second transition series includes the elements from yttrium to cadmium. While the third transition series includes the elements from lanthanum to mercury. By definition, transition elements are those that have incompletely filled d orbitals either in their elemental state or in any one of their chemically significant oxidation states. Thus, the elements zinc, cadmium, and mercury, which have D10 configuration, both in their elemental and in their stable oxidation states, are not considered transition elements. The general electronic configuration of these elements is N-1 D1 to 10 Ns1 to 2. This generalization has several exceptions, because the energy difference between the Ns and N-1 d orbitals is less, and the transition of electrons between Ns and N-1 d takes place readily. Furthermore, atoms of the d block elements try to fill their available d orbitals either partially with 5 electrons or completely with 10 electrons whenever possible. This is due to the fact that half-filled or completely filled orbitals impart greater stability to an atom because of the greater exchange energy. A consequence of this factor can be seen in the electronic configurations of chromium and copper in the 3D series. Chromium, for example, has a configuration of 3d5 4s1 instead of the expected 3d4 4s2. Copper, on the other hand, has an electronic configuration of 3d10 4s1 instead of 3d9 4s2. The properties of transition elements depend largely on their electronic configurations. Thus, with partly filled d orbitals, these elements exhibit certain characteristic properties, like display of a variety of oxidation states, catalytic properties, alloy forming ability, complex forming ability, formation of colored hydrated ions and salts, and para- and ferromagnetic properties. The precious metals like gold, platinum, and silver, and industrially important metals like iron, copper, and titanium form part of the transition elements. The electronic configurations of the d block elements differ only in the number of electrons in the d orbitals of the penultimate shell, while the number of electrons in the valence shell remains the same. Thus, they have many physical and chemical properties in common. Nearly all the elements exhibit typical metallic properties. Let us review some of them in detail. First, let us look at the metallic character. As the number of valence electrons in these elements is very small, all of them are metals. They are good conductors of heat and electricity. They exhibit metallic luster and are hard. They are malleable and ductile. They form alloys with other metals. They have one or more typical metal lattice structures as shown in the table here. Like beryllium and magnesium, with which they are isostructural. Their structures deviate from perfect hexagonal close packing by elongation along the six-fold axis. Mercury is a shiny liquid at ordinary temperature. Melting and boiling points. The melting and boiling points of the transition elements are generally high. The melting points of 3D, 4D and 5D transition metals are depicted in the figure here. As you can see, in any series, with the exception of anomalous values for manganese and technetium, the melting points first increase to a maximum at D5 configuration and then gradually decrease towards the end of the period. The high melting points of these elements are attributed to the participation of a greater number of electrons from n-1 d orbitals in addition to the ns electrons in the interatomic metallic bonding. Now let's look at the atomization enthalpies of these elements. These elements have high enthalpies of atomization. The trends in the enthalpies of atomization of these elements are shown in this graph. From the graph, you can see that they exhibit maxima at about the middle of each series. The maxima in each series indicate that interatomic interactions are stronger in half-filled d orbitals. It means that the greater the number of unpaired electrons, the stronger are the interatomic interactions and the stronger is the bonding between atoms. Consequently, the higher are the enthalpies of atomization. Enthalpy of atomization is an important factor in determining the standard electrode potential of a metal. Hence, metals with high standard electrode potential tend to be noble in their reactions. For example, copper, due to its high enthalpy of atomization, exhibits noble character. You will also note from the graph that the metals of the second and third transition series have greater enthalpies of atomization than the corresponding elements of the first series. This factor accounts for the occurrence of frequent metal-metal bonding in compounds of heavy transition metals. The atomic radii of elements in the 3D series are given in the table. You can see from the table that the atomic radii of the elements show a progressive decrease in radius with an increase in atomic number. This is due to the fact that an increase in the nuclear charge tends to attract the electron cloud inwards. You already know that d electrons offer poor shielding effect. Hence, the nuclear charge attracts all the electrons more strongly, resulting in a contraction in size. However, the variation within a series is quite small. The same trend is observed in the ionic radii of a given series. The atomic radii of the 3D, 4D, and 5D series of elements are given in the form of curves for comparison. You can see that although the atomic radii increase from 3D to 4D, the atomic radii of the 4D and 5D transition series are very close. This is due to the fact that the 4f subshells fills up before the 5D orbitals, which results in a regular decrease in atomic radii. This steady decrease is called Lanthanide contraction. The consequence of Lanthanide contraction is that the radii of the second and third transition series are similar. For example, zirconium and hafnium, niobium and tantalum, molybdenum and tungsten, technetium and rhenium have close atomic radii, and, therefore, have very similar physical and chemical properties. Like in any transition series, the imperfect shielding of one electron by another in the same subshell is responsible for lanthanide contraction. However, the shielding effect of one 4f electron by another in the same subshell is less than that of one d electron by another, because of the diffused shape of the f subshell. Thus, with an increase in the nuclear charge at each step, there is no comparable increase in the mutual shielding effect of 4f electrons. As a result, the electrons in the outermost shell experience increasing nuclear attraction from the growing nucleus. Consequently, there is a fairly regular decrease in the size of the entire 4Fn orbitals. A decrease in the metallic radius, along with an increase in the atomic mass, results in a general increase in the density of these elements. Thus, there is a significant increase in the density from titanium to copper. One of the most striking features of the transition elements is their ability to exhibit several oxidation states in their compounds. This unique ability is due to the small difference in energy between the ns and n-1d orbitals. Because of this, in addition to ns electrons, n-1d electrons also participate in bonding. The table here lists the common oxidation states exhibited by the first row transition elements. Note that the oxidation states shown in brackets correspond to unstable oxidation states. Some points may be noted from the table. Except for scandium and zinc, all the other elements show more than one oxidation state. Scandium, due to the availability of very few electrons for bonding, does not show variable oxidation states. On the other hand, zinc, due to the presence of too many d electrons, has fewer orbitals available for bonding, and thus does not exhibit variable oxidation states. The elements from titanium to zinc, with the exception of copper, show a minimum oxidation state of +2. Copper shows a minimum oxidation state of +1. The maximum oxidation state is given by the sum of the s and d electrons for the first 5 elements. For example, scandium, titanium, vanadium, chromium, and manganese exhibit maximum oxidation states of +3, +4, +5, +6, and +7 in the form of their oxides, oxyanions and oxycations, as shown here. The maximum oxidation states of the elements after manganese are not at all related to their electronic configurations. For example, cobalt shows only +2 and +3 stable oxidation states. The relative stabilities of various oxidation states of 3D series elements can be correlated with the extra stability of 3D0, 3D5, and 3D10 configurations to some extent. Thus, a titanium 4+ ion with 3D0 configuration is more stable than a titanium 3+ ion with 3D1 configuration. Similarly, a manganese 2+ ion with 3D5 configuration is more stable than a manganese 4+ ion with 3D3 configuration. The transition elements exhibit oxidation states that differ from each other only by 1 unit. This is in marked contrast to the S-block elements, which exhibit only the group valency, and the P-block elements, which exhibit either the maximum group valency or a valency less by 2 units. For example, manganese exhibits all the oxidation states from +2 to +7, which differ from each other by unity. On the other hand, tin and lead, which belong to group 14, exhibit oxidation states of 2 and 4. You know that in p-block elements, lower oxidation states are favored by heavier elements because of the inert pair effect. But in d-block elements, higher oxidation states are more stable for heavier elements. For example, in group 6, molybdenum 6 and tungsten 6, in the form of their oxyanions, are found to be more stable than a dichromate ion, in which chromium is in its highest oxidation state of 6. Thus, a dichromate ion acts as a strong oxidizing agent in an acidic medium, while the oxyanions of molybdenum and tungsten do not. Some transition metals also show zero oxidation states in complexes like carbonyls, where the ligand acts as a pi acceptor. Nickel tetracarbonyl and iron pentacarbonyl, shown here, are two examples of a transition metal in zero oxidation state. In the lower oxidizing states, these elements form ionic compounds. For example, manganese 2 oxide and chromium 2 oxide are ionic in nature. The tendency to form ionic compounds decreases with an increase in the oxidation number of the metal. Higher oxidation states give rise to covalent compounds. For example, manganese 2 oxide is ionic. Manganese 4 oxide is intermediate between ionic and covalent. And manganese 7 oxide is purely covalent. As the oxidation state of the transition metal increases, the charge density on the metal also increases. This results in an increase in the polarization of the anion charge cloud by the metal, and hence, the covalent character increases. The acidic nature of the oxides increases with an increase in the oxidation state of the transition element. For example, manganese 2 oxide is basic, manganese 4 oxide is amphoteric, while manganese 7 oxide is acidic in nature. Similarly, chromium 2 oxide is basic, chromium 3 oxide is amphoteric, and chromium 6 oxide is acidic. A gradual change in nature of the oxides from basic to amphoteric can be clearly seen in vanadium. Vanadium 3 oxide is basic, while vanadium 4 oxide is less basic. On the other hand, vanadium 5 oxide is amphoteric with more acidic properties. Vanadium 5 oxide reacts with alkalis to give orthovanadiate ions, and with acids to give dioxovanadium 5 ions. In higher oxides, the acidic character is predominant. Thus, manganese 7 oxide gives permanganic acid, while chromium 6 oxide gives chromic acid and dichromic acid. The table here shows the observed and calculated values of the standard reduction potentials for the reduction of M+2 ions to their respective metals. It also shows the thermochemical data related to the transformation of the solid metal atoms to M2+ ions in solution. The calculated values of the potentials are those based on the standard enthalpies of formation of the +2 ions in an aqueous solution. The plots of the experimental and calculated values of the reduction potentials are shown in the figure. The curve in red corresponds to the observed values, while the one in black corresponds to the calculated values. The plots indicate that the experimental and calculated values are in close agreement with each other. The M+2 to M reduction potentials have enthalpic contributions from the terms in the equation shown here. The equation indicates that the magnitude of the reduction potential is governed by the values of three relatively large terms: the negative enthalpy of hydration of M2 plus 840, the sum of the first and the second ionization enthalpies, and the smaller term enthalpy of atomization. The interplay between these three terms decides the value of the reduction potential. The irregularity in the variation of electrode potentials is due to the irregular variation of the ionization enthalpies, and also the hydration energies of the divalent ions of these elements. All those elements with negative reduction potentials act as strong reducing agents and liberate hydrogen from dilute acids. For example, titanium 2+, vanadium 2+, and chromium 2+ ions act as strong reducing agents and liberate hydrogen from a dilute acid, as shown in the equations here. On the other hand, copper, with a positive reduction potential, does not liberate hydrogen from dilute acids. Thus, copper is inert towards non-oxidizing acids such as HCl, but reacts with oxidizing acids such as nitric acid and hot concentrated sulfuric acid, as shown here. The reason for this behavior is the high energy needed to transform solid copper to gaseous cupric ion, which is not exceeded by the hydration enthalpy of the ion. The general increase in the ionization energy sum is dominant in deciding the trend towards the less negative values of the M+2 to M reduction potentials. It is interesting to note that the values of the reduction potentials for manganese, nickel, and zinc are more negative than expected. The electrode potential values of manganese and zinc can be explained on the basis of the stability of the half-filled D subshell in Mn2+, and the completely filled D10 configuration in zinc 2+ ion. The stability is due to the maximization of the exchange energies between electrons of like spin. The electrode potential for nickel is related to the highest negative hydration enthalpy corresponding to its smaller radius. Now let us look at the trends in the standard electrode potentials of M+3 ions to M+2 ions. Not all the first row transition elements have the same pairs of stable oxidation states. The elements from vanadium to cobalt are chosen because they all have +2 and +3 states, for which reliable experimental data are available. The observed electrode potentials for these elements are shown in the table here. The lower value for vanadium is due to the stability of V2+, as it has a half-filled T2G level. Manganese has a higher electrode potential value than chromium and iron because of its very high third ionization energy, which is again due to the stability of the half-filled D5 configuration. The higher values for manganese and cobalt show that they are the strongest oxidizing agents in aqueous solutions. The comparatively low value for iron shows that the reduction of ferric ion to ferrous ion is less favorable, since ferric ion is extra stable due to the half-filled D5 configuration. Let's now look at the trends in stability of the higher oxidation states of these elements. The table here lists the stable halides of the 3D series of the transition elements. can be seen from the table, titanium tetrahalides, vanadium pentafluoride, and chromium hexafluoride have the highest oxidation numbers. The highest oxidation state, +7, for manganese is not seen in simple halides, but MnO3F is known. Beyond manganese, no metal has a trihalide, with the exception of cobalt trifluoride and the trifluorides, trichlorides, and tribromides of iron. Fluorine stabilizes higher oxidation states either because of its higher lattice energy, as in the case of cobalt trifluoride, or higher bond enthalpy, as in the case of vanadium pentafluoride or chromium hexafluoride. Thus, vanadium pentafluoride is stable, while the other halides undergo hydrolysis to give oxohalides of the type VOX3. Fluorides are unstable in their lower oxidation states, and, therefore, chlorides, bromides, and iodides exist in +2 oxidation state, while fluorides do not. Copper, in +2 oxidation state, forms all the halides except iodides, because cupric ion oxidizes iodide to iodine. Copper +1 compounds, being unstable in aqueous solutions, undergo disproportionation to give stable cupric ion and copper, according to the equation shown here. The stability of Cu2 plus ions rather than Cu plus ions is due to the higher negative hydration enthalpy of cupric ion than cuprous ion, which more than compensates for the second ionization enthalpy of copper. Now let's look at the higher oxidation states in oxides. The table here lists the oxides of the 3D series of elements. The highest oxidation number in an oxide coincides with the group number and is attained from scandium-3 oxide to manganese-7 oxide. No higher oxides are seen beyond manganese. For example, the only stable higher oxide formed by iron is iron-3 oxide. Although iron forms ferrates in alkali media, in which iron is in +6 oxidation state, it readily decomposes into iron-3 oxide and oxygen. Apart from oxides, oxygen also stabilizes higher oxidation states in the form of oxocations. For example, vanadium-5 is stabilized as dioxovanadium-5 ion, vanadium-4 as oxovanadium-4 ion, and titanium-4 as oxotitanium-4 ion. Oxygen exceeds fluorine in its ability to stabilize higher oxidation states. Thus, the highest manganese fluoride is manganese tetrafluoride, while the highest oxide is manganese heptoxide. The ability of oxygen to form multiple bonds with metal atoms is responsible for its superiority over fluorine in stabilizing higher oxidation states. This ability can be clearly seen in the covalent oxide, manganese heptoxide. In this compound, each manganese atom is surrounded by 3 doubly bonded oxygen atoms, including an MnO-Mn bridge. Similarly, oxygen also forms double bonds in the tetrahedral MO4N- ions, known for vanadium-5, chromium-6, manganese-5, manganese-6, and manganese-7 ions. Most D-block metal compounds are colored in their solid or liquid states. Color is associated with the ability of a compound to promote an electron from one energy level to a higher energy level. In the case of transition metal ions, under the influence of ligands, the degeneracy of the 5d orbitals is lost, and they separate into two distinct energy levels. One set, known as the EG set, consists of two orbitals, dx square minus y square and dz square. The other set, known as T2G, when white light is incident on a transition metal ion, the electron in the lower energy d orbital set absorbs certain radiations and gets promoted. The transmitted radiation, devoid of the absorbed radiations, is the complementary color of the absorbed light. This complementary color, for example, hydrated Cu2 plus ions, absorb radiation of wavelengths corresponding to red light and transmits its complementary color blue. The colors of some hydrated ions of the 3D series of elements are given. Now, let us look at the magnetic properties of d block. Substances, depending on their behavior in an external magnetic field, are classified into paramagnetic and substances that are weakly attracted to a magnetic field are called paramagnetic substances, while substances that are repelled are called. Paramagnetic behavior is caused by the presence of unpaired electrons in the atom, ion, or molecule. Diamagnetic behavior is caused by the absence of unpaired electrons. Every unpaired electron is regarded as a micromagnet with a certain value of magnetic moment. The magnetic moment of the electron is due to spin angular momentum. However, for 3D series of elements, the orbital angular momentum of the electrons is small, and hence, its contribution in these elements can be ignored. Therefore, the observed magnetic moment, the magnetic moment for these elements is determined by the spin-only formula. Mu is equal to square root of n multiplied by n plus 2. Here, n is the number of unpaired electrons and mu, when n is equal to 1 magnetic moment, is equal to 1.73 Bohr magnetons, and when n is equal to 2, we get 2. In case of iron, cobalt, and nickel, the unpaired electron spins are much pronounced. As a result, these elements are much more paramagnetic than the rest of the elements.